Lecture 1, Inventory Control with Known Demand, Chapter 4 of the textbook, Part 5. EOQ extension to a finite production rate, EPQ, or economic production quantity. In the EOQ basic model, we assume that we are ordering our requirements to an external supplier, and that external supplier will deliver the entire order at the same time. But what if we produce the parts internally in our factory? And in this case, if the production rate is not infinite, I mean, if the production rate is much higher than the demand rate, then in that case we can assume that the production rate is infinite, and still we can apply EOQ model because it will work in that situation. But since that's not again gonna happen in the real world, the production rate is limited. So in this case, when we place an order and we start producing the orders, it will take a while to produce all the Q quantity, and then we're not going to receive the the entire queue at the same time. We will receive as production goes ahead, so continuously over time. So it will take a period of time that we will continuously receive the order quantity. So in this case, we have the EPQ model. So this is the inventory level for the case of EPQ. So at this time, let's say we place our order, and since the production rate is P, so here we do have the production rate as P, so it takes a while to produce the Q units. So in the meantime that we are producing the Q units, we do have demand as well, right? So we can say we are receiving the orders in our inventory with the rate of P, and at the meantime we are selling our goods with the rate of lambda. So in that case, with the rate of P minus lambda, the inventory level will be increased, right? So yeah, with this slope, P minus lambda, the inventory level starts increasing until at the time that we stop production. I mean, we have produced Q units, so the production is stopped at this time. So in this case, the first period in each cycle is called T1, and it's up time, the time that we produce the goods. So it's called production time as well. Since we want to produce Q units and the production rate is P, so the time to produce Q units will be Q divided by P, right? So yeah, the uptime T1 will be Q over P. So here we stop production, so we do have now H units in our inventory. We call this as the height here, which will be the maximum inventory level that we will have in our stock, okay? And then from here, we don't have production, but we just have demand. We are satisfying demand from our inventory, so the inventory level will be decreased with the rate of lambda, right? And again, at this time, it will be the second cycle. We place our order and we start again producing the goods with the rate of P, and again we do have demand as well, so demand rate is lambda. So with the rate of P minus lambda, again demand, again inventory starts increasing up to H, and the same for the later cycles. So here T is our cycle here, and as you see, it includes two subperiods. T1 is uptime, production time, it will be Q over P, and T2 is a downtime. There's no production in this period, it's T minus T1, okay? So in EPQ model, our order size is Q here, and so and the demand is lambda, so it's obvious that lambda over Q will be the number of orders that we do have per year. And if we multiply this by K, the setup cost or the ordering cost, it will be the average annual setup cost, same as EOQ model, right? No difference here. But for the average annual holding cost, so this is actually our inventory level behavior. So as you see here, the height here is H, and the cycle time or the base here is T, right? So the area for this triangle will be half times H times T, right? So that's for one triangle over here, and as you know, this is for one cycle, right? And per year, the number of cycles per year will be 1 over T, right? So if we multiply this by the number of cycles, which is 1 over T for the year, then it will be the average inventory level or area under the inventory level per year, right? So now we do have these, the T is canceled, so we will have half times H. So this is actually the average inventory level per year, okay? And then if you multiply this by, little h, which is the inventory holding cost per unit per year, that will be the average inventory level, average inventory holding cost per year, okay? So, but for the maximum inventory level, capital H here, let's see how we can obtain that. So, as you see here, this slope is P minus lambda, right? And this height here is H, and here this base is a T1, which is Q over P, right? So for this triangle, let me show with a different color here. So for this triangle here, the slope P minus 1 will be H, the height, divided by the base, which is Q over P, right? So by having this, we do have this equation here, H, the height equals Q times 1 minus lambda over P, okay? So by having that, if we replace H by Q times 1 minus lambda over P on the average annual holding cost, so we'll have this, and at the end we reach to this equation, have Q times H prime. So we can say here in EPQ model, the average annual holding cost is the same as EOQ in the shape, in the structure, it's this, the same as EOQ, but instead of H here, we do have H prime, and H prime equals H times 1 minus lambda over P, okay? So the order quantity or order size here, QSR, becomes this, square root of 2k lambda over H prime, exactly the same as EOQ, but instead of H, we do have H prime, and H prime is this, H times 1 minus lambda over P. And here we assume that P is greater than lambda, because other than that, the system will be infeasible. So the production rate should be greater than the demand rate in order to have a feasible system, okay? So yeah, that's the EOQ model, the EPQ model here. And so the cycle length, same as before, would be Q over lambda. The uptime period or production time T1 will be Q over P, and the downtime will be T minus T1. That's it. This is all about the EPQ model, okay? Let's have an example here. A local company produces an erasable, programmable, read-only memory, EPROM, for several industrial clients. So it has experienced a relatively flat demand of, so here lambda equals 2,500 units per year for the, yeah, and the APRAM is produced at a rate of 10,000 units per year. So here P equals 10,000 units per year. The accounting department has estimated that it costs $50 to initiate a production run. This means K here, the setup cost is $50, and each unit costs the company $2. So the C here is $2, and the cost of holding is based on a 30% annual interest rate, and so I here is 0.3. So H becomes 2 times 0.3, which will be 0.6, and so H prime, we need at first to calculate the H prime here. So the H prime will be H times 1 minus lambda over P. So it will be 0.6 times 1 minus 2,500 divided by 10,000. So it will be 0.45. Okay, so by having this data, we can calculate the EPQ here. So the EPQ will be this 2K lambda over H prime, right? So it will be 745 units. Okay, so by having this quantity for production, then we will have these quantities. So the cycle time here will be T equals Q over lambda. So it will be 745 divided by 2,500, it becomes 0.298 years. So this means every 0.298 year we will have a cycle of production and selling the I mean a cycle of uptime and downtime for our inventory system. Okay, and so the uptime or production time T1 will be Q over P. So 745 divided by 10,000, it will be 0.0745 year, and the downtime cycle T2 will be T minus T1, so it will be 0.2235 year. Okay, and the average annual holding cost and inventory cost, I mean ordering and holding cost GQ star here will be this 2 K lambda H prime, so it will be 335.41 dollars. Okay, and the maximum inventory level H here will be Q star times 1 minus lambda over P, and it will be 559 units. Okay, so this is the maximum inventory level in our stock. So yeah, as you see, everything is the same as EOQ, but just consider H prime instead of H, and also we can calculate the uptime period and the maximum inventory level and so on. Okay. Let's have a discussion here. If we assume that there is an external supplier for this part, that we are not going to produce this in our factory, in that case, we will go with EOQ, right? Not EPQ. So if we go with EOQ, then the order quantity size becomes this, 645. But if we're going to produce it in our factory with a limited P production rate, then the EPQ size becomes 745. So as you see here, the QSR for the EOQ with the same data is always smaller than the EPQ. So is that the case? I mean, should actually EOQ be smaller than EPQ in all times with the same data? The answer is yes. So the reason here, the Q star, let's say EOQ is this 2K lambda over H, right? And the EPQ is 2K lambda over H prime. So as you see here, K and lambda are exactly the same, and just the difference here is H and H prime, and H prime is H times 1 minus lambda over P, which is always less than H, right? So since H prime is always less than H, so because of that, EPQ will be always greater than EOQ, okay? Another extension that we can have for the basic EOQ model is considering quantity discount model. So yeah, in the real market, suppliers usually offer promotion plans with encouraging their customers to order more and more. So yeah, the purchase price then is not independent from the order size. So by having different order size, you may have a different level for unit purchase price. Okay, so usually we do have two types of quantity discount models. The first one is all units discount. So in this case, we do have different levels, and if we increase our order size to the next level, then the entire order will be based on the new purchase price with the discounted purchase price. So the discount is applied to all of the units of the order. But in the incremental discounts, the discount is applied just on the units above the break point. So we do have some thresholds, some levels, and if we go over a level for order size, then the discounted price is applied just for the units above that break point. Okay. So in all units quantity discount model, as you see here, for example, if the Q order size is less than 500, the purchase price is 30 cents. But if we go over 500 up to 1,000, the purchase price will be 29 cents, 1 cent discount here. And if we go beyond 1,000 units, the purchase price will be 28 cents for all units, right? This is all units discount model. But in the incremental, as you see here in this shape, the discount is applied just on the units above that threshold. So here, if Q is between 0 to 500, then the purchase price is 30 cents. Okay. If we go over 500, the first 500 will be based on 30 cents, and the units over 500 will be based on 29 cents. And again, if we go over 1,000, then the first 500 will be based on 30 cents. The second 500 will be based on 29 cents, and the units over 1,000 will be based on 28 cents. So this is called incremental quantity discount model. So in the next part, we will have the detailed models for all units and incremental discount models. Okay, thank you.